I have to apologize. It's not the title I gave. I figure out I'd be better off showing this thing because it's kind of betterly contained in 30 minutes. It's kind of different from stuff that you guys are doing, but I hope you'll find some interest in it nevertheless. So I just want to kind of define the main object I'm working with. So it's a graph, but it's has a little bit more structure than that. So it's what we call a simplicial complex or a triangulation. So it has vertices and edges, but it also has faces. And the rule is that this thing defines a topological two-surface, which means that every edge is connected exactly to two triangles. And every star, every one ring of a vertex is homomorphic to a disk in the plane. So this defines that this thing is basically a surface, and we use it to model surfaces. For example, this is a particularly famous surface that people like to show. And the problem I would like to discuss is we're giving two such polyhedral surfaces, so two such triangulation, and some sparse set of vertices which are colored, so meaning that they are corresponding in some sense because someone thought that these are corresponding. And our goal, the task, is to compute a map which is a homomorphism, which in this context it's like a one-to-one, an onto map between the two surfaces, which are continuous, and the inverse is continuous, but the mathematical is not very important because we're going to just use like simplicial finite stuff. So we're just looking for a map that takes every vertex here to some place on this triangulation, and we are required that no two points are going to map on the same location on the right-hand side, and that the whole right triangulation will be covered. So here is a visualization of the output of the algorithm that they're going to present. The way we're going to visualize it is that we're showing some texture here, and we just transfer it by this map that we compute, and you kind of appreciate the fact that it looks homomorphic. It maybe has other properties. So this is the problem. It's a very kind of standard problem. The main difficulty, it's like an interpolation, right? Like you have several points of data, and you want to transfer a function through those points. The main difficulty in this type of problem is that the target domain is not a straight Euclidean space. So the fact that you want the image of every point here to lie here is a non-convex problem because this shape is not convex. So the question is how to address that computationally. One thing that people have been doing in order to do that is to transfer the problem to a space which is easier to handle, like the plane. And the way that it is done is that, for example, if you have something like a sphere in 3 dimensions, okay, you can think that this is a triangulation. I'm not going to show triangles anymore, but topologically it doesn't matter. It's the same. So we have a sphere, and we have this bunch of points. This is like the first surface. We have a bunch of points. So what we're going to do, we're going to construct a tree. So this, I'm assuming that this whole talk, I'm just going to talk about genus 0 surfaces. So something which topologically looks like a sphere. No handles, no boundaries, and so on. So we construct a tree through these points, and now we take a pair of scissors, and we cut along the edges of this tree. And the property, it's a topological property, but it's kind of intuitive for us to see that if you cut it along those edges, you're going to get something which is topologically a disk or a planar graph, right? And you can flatten it homomorphically to the plane. For example, Tat's embedding gives such a realization to this graph. But we're not interested in an embedding. We're interested in a good embedding, which means that we want to do that. We want to look for this map, which is a simplicial map. It takes every vertex to a vertex on the plane. And we have some energy that among all these flattening is going to choose one which is favorable. So, for example, what kind of energies people like in this field? So let me define exactly how we define an energy on this triangulation. So we have like a piece, like this is a star, a one ring in a 3-dimensional space, and we have a triangle marked by T. We're going to map the vertices to the plane, and when we restrict this map to the triangle, it's just going to be an affine map, taking this planar triangle to this planar triangle. Okay. So the energy of such a simplicial mapping, we can call it simplicial mapping phi, can basically sum, it's like integrate, can sum the distortions or some quantity over those affine maps, triangle by triangle. And here we multiply by the area of the triangle. So this is some kind of integrated quantity. For example, what is a canonical example of a choice of an energy per affine map? So how do we measure an energy per affine map? So something that is popular is to measure the conformal distortion. It's like the anisotropic scaling that you do to a triangle. So just a kind of a reminder, if you have two planar triangles, there's a unique affine map between them. You take the linear part of the affine map, you're presented in arbitrary orthogonal coordinates, you get a 2x2 matrix. 2x2 matrix always take a circle to an ellipse, and the aspect ratio of this ellipse is called the conformal distortion. Okay, so affine map takes circles to ellipses, and the question is how strong anisotropic the ellipses are, and we want to minimize that. Okay. So okay, it's a good energy because we know, for example, that surfaces can be flattened conformally to the plane. So this is kind of a discrete counterpart, but let's just kind of take it as a good energy. And now a naive solution to the problem I presented is the following. So you take your two surfaces. These are two triangulation. Disregard for a second the texture that is shown on them. These are the points. You see, for example, the ears of the piggy goes to the ears of the calf or whatever. We constructed a tree that spans these points. Now, each of these things are mapped. We're cutting them open, the triangulation, and we map both of them to some domain in the plane. And it kind of marked by, so if this edge is red, since we cut it, it duplicates twice. Every edge duplicates twice, so we have two copies of each edge, two copies of the red one, two copies of the blue one, and so on. And the mapping is defined by just taking phi, which is homomorphism, composed with psi minus 1. So this is a way to construct this homomorphism, and it satisfies, it is a continuous. You can also check it continuous by kind of thinking a little bit about what it means when you go to a boundary point. It satisfies the interpolation property because the points are mapped to the same planar locations. Okay. The problem with these type of methods is that after we cut the surface, we kind of lose the point of view that we actually worked with a closed surface. Okay, so in some sense, what happens from the two sides of the seam is kind of already independent. What happens in practice, so I'm showing you like a practical problem, you can see that from two sides, if you take some isolines here and you map them, you can see that from two sides of the seam, you get a very different behavior. And it's not really surprising because this thing is not really topological. It's not topological equivalent to this. This cut is not forced to behave like this cut in any sense. So this is a problem. This is a solution that people use, but it often produces something which is unsatisfactory. And what I wanted to present is something that's going to make this point of view in some sense seamless. That's the goal of my talk, so I'm going to describe it now. So the goal is to produce what I'd like to state as a seam-invariant surface mapping, which means that from the point of view of computer scientists, maybe you'll relate to the following definition. If someone provides you the map between the triangulation, you will not be able to reverse engineer the cuts from it. So it will be, you have no information about the cuts from the final product of the algorithm, okay? In other words, from two different cuts, I'm going to define this precisely in a second, from two different cuts. So if I cut, instead of this cut, I'm going to take this cut, yeah, which is homotopic to that cut. The final map can still be reproduced by that cut, exact same mapping, okay? So for example, the output of the algorithm on this example is this thing, and you can indeed could see at least intuitively that if you take some function, you look at it as isolines and transfer it to this surface by this map we computed, then the map kind of is indifferent to the cut. You don't see any special behavior or bias around the cut. So that's the goal. Now, the solution to this problem is it's rather simple, and it's by introducing a certain type of planarization of planar graphs, which we'd like to call G flattenings. Okay, so G is a group, which I'm going to define in a second. And basically, the G flattening is different from, so this is just a regular flattening. You take a disk type triangulation, you just flatten it somehow, you don't care. What we suggest is that instead of doing that, we take a group. In particular, we take a group which is a subgroup of the affine motions. For example, translations, rotations, and scaling, like similarities, okay, in the plane. So rotation, isotropic scale, and translations. That's the subgroup for affine motion. And we choose it such that the energy is invariant to composition with that group. For example, if we said that we take a triangle to the plane and we measure the conformal distortion, then if we further take this triangle, rotate it, and translate it, or uniformly scale it, we do not change the aspect ratio of the triangle. So it means that if we take, for example, G to be the group of similarities, then the energy I define to be the conformal energy is invariant to that. So again, you can flatten a triangle, you can rotate it, scale it, translate it, you won't change its aspect ratio. So this specific group is matching to the energy I defined, and it has this property, okay? So once we set this group, now we want to define the G flattening. It's very simple. It's a regular flattening, except that the boundaries, let's forget about the local injectivity for a second, all require that if we have two pieces of boundaries that came from an edge on the surface, so I remind you, when you cut a surface, every edge is duplicated twice. So the planar realization of these two edges should be related by an element from the group. So here it's not just illustration, it's done like that. So for example, if you look at this blue edge and the other side of the blue edge, you see that they are related by a similarity. Yeah? You see it's like a scale and a rotation. And also you can look at the yellow thing, which looks like a scale and rotation. And what we claim is that if you compute such a flattening, when you minimize this conformal distortion energy, and you make sure that the boundaries have this relation, then in some sense you did something which is seamless. And I'm going to put a little bit more justification into this statement in a second. So that's the definition. That's a G flattening. Again, G is like the group, which is invariant to the energy we are minimizing to create the flattening. So here's a real example. For example, we take a sphere. This is a triangulation of a sphere. We take 3 points on the sphere, and we cut it very simply like this. So it's a very simple tree. It's like a path. And now, after we cut it, we flatten it. We minimize the conformal distortion. And this, you see, it looks kind of nice. That's not it's not like any coincidence. That's like how discrete conformal maps look like. Every triangle behaves almost like a similarity. It cannot be perfect in the discrete case, but it feels like every triangle only scales and rotates. But anyway, the important thing is that the boundaries are related by a perfect similarities. So you see that this boundary is a perfect similarity of this boundary. You see this small bump here matches perfectly to this small bump. And what do I mean that this image is now it's kind of almost indifferent to the cuts? In what sense it's different to the cuts? If I take a homotopic version of the cut, so if I take, for example, a very simple, very similar cut, but instead of going from this side of these two triangles, I take a cut which go from the other side, what I mean is that I can realize the flattening by just taking two triangles that match, so the two green triangles here, and move them by the similarity to the other side. Now this procedure produces a mapping which has exactly the same energy, okay? Because I use something which is invariant by construction. So this mapping that realizes this cut, which is homotopic to this cut, it has exactly the same energy level. So in that sense, you can see that if I change homotopically cuts on the surface, I can use these transition functions to create a suitable mapping. Okay, and now why is that useful? So what we're going to suggest is that you take your two surfaces, visualized here as spheres, because it's really a topological thing, it doesn't matter. We marked here, there's like 5 corresponding points, and we cut the points using isomorphic trees. You see, so these are two isomorphic trees that go through those points. And what we'd like to do is to flatten both of them using G flattenings, such that the points are mapped to the same planar locations. So what you see on the right-hand side here is an overlay of the two flattenings. The yellow goes to the yellow and the blue goes to the blue. Some are overlapping and some are not. And what I want to claim is that although this image is not perfect one on top of each other, like my naive solution, it still defines a unique mapping, which is homomorphism between the surfaces. And I'm going to explain why. Before I do, I just want to highlight a property of these flattenings, is that because we're talking about similarities and the points are mapped to the same locations, then basically, you know that similarities are uniquely defined by 2 points on the plane that goes to arbitrary 2 points. So if I fix 2 pairs of 2 points that uniquely define a similarity, then what we have here is that any domain that is bounded by 2 curves related to corresponding cuts are related by a similarity, the domain. So what we have here is some sort of a puzzle structure. You see that every piece that is outside in the XOR of the 2 domains is related by a similarity to another piece. And what we can do, we can just play a game where you cut the pieces and match them. For example, this blue piece going to match to this orange piece, so we can cut it. And here it's a kind of a visualization. You can cut it and stitch it there. And you can continue in this manner until you reach a situation where both of the maps are mapping exactly the same domain. When they map exactly the same domain, we can do basically the composition of the maps to achieve the homomorphism between them. So maybe I'm going to skip. So let me just, I'm just going to recap. So the point is that if you take 2 surfaces with marked points, you construct isomorphic trees and you map them using G flattenings that take the landmarks to the same planar location, you can define a map, a homomorphism between them. Now what I need to convince you is that this map is basically, does not hold any information about the cuts themselves. So you can basically realize this map with any set of homotopic cuts, or alternatively, if I give you the map, you won't be able to reconstruct the cuts after the fact. There's topological issues about, okay, let's leave that. In practice, I just want to say that algorithmically, there's no need to actually cut and paste. That's kind of just an intuition. You can produce a lifting algorithm that just take a spanning tree of 1, and every time it crosses an edge, you just jump by the similarity. There's no need to actually cut the thing. So it's not. So what we want to do is to compute a mapping. We can look for 2 G flattenings of the 2 surfaces after they cut to a trees. So you want to map them by minimizing this conformal energy. We can take the sum. You can take whatever you want, the maximum. It doesn't matter. And under the constraint that these 2 satisfy these conditions. So they're both G flattenings, and they take the points to the same planar location. And now the claim is that we get a seamless mapping. And here's the formal definition of what seamless means. So I'm just going to say it. I'm not going to read it. So it says that basically, if you take your 2 surfaces with the points, and now you produce a different cut, which is homotopic to the original cut. So you can take a cut, and instead of going straight, you can do a very big circle. Doesn't matter. If you can produce an evidence in terms of 2 new G flattenings that satisfy the conditions and define the same map, okay, then basically it means that you're seamless, because every homotopic set of cuts can produce exactly the same map in terms of energy and functional correspondence. So every point would map to exactly the same point. So this means that basically you would never be able to tell which cuts produce the exact map. And it's not, I hope it's clear by this point that by construction this is almost be true. You need to prove it a little bit, but it's kind of, it should be intuitive at this point, because if you change the cut, you can just change the G flattenings accordingly, but the operation by which you change the G flattening, taking the similarity and activate them, it's exactly the way you define the map. So it kind of would cancel out, and you would achieve a seamless mapping. Okay, so I'm not a theoretician, so we have a lot of things to do after the idea, after we get a paper, because there's a lot of implementation goes on. Maybe I'm not, so I think there's nice parts related to how to do that, how to cast it as a practical optimization problem, but let's not talk about that. I just want to show you some beautiful pictures and send you to lunch. So for example, one sanity check that you can do, you can take a sphere, you know, all the conformal automorphisms of the sphere are the Mobius transformations. So we can compute analytically a particular Mobius transformation that interpolates 3 points. So take these 3 points to these 3 points. And now we can, so this is analytical computation. The reason you see here like polygons, we just use the finite mesh here, but it's really an analytical map. So you can take 3 points, you can cut them. We just produce different cuts, and you produce, and at least you see that the algorithm reproduces this map regardless of how you chose the cuts and so on. Maybe a more, okay, never mind about that. Here's a different thing. So we take these two surfaces, two triangulations. It's a little bit hard to see, but there are a lot of matching points. Here you see, for example, one cut that goes kind of above the cheek, and here's a cut that goes under the cheek, but it's still homotopic. You can continuously change one to another, but it produces exactly the same mapping. Okay, and more result and more result. I think it's interesting to talk about higher genus, but maybe next time. Okay, I'll make a small comment. So I'll always mention that the change of cuts, homotopic change of cuts, does not change the map. So what do they change? So what I want to claim is that the choice of cut up to homotopic relation kind of decide the homotopic class of the map. So you can change the cuts continuously without crossing each other, but you can do something which is not homotopic, like taking one cut and move it from the other way that there's no continuous way you can take this yellow cut to this yellow cut. This necessarily would produce a mapping which is not homotopic to the first one. So these are two mappings of the punctured sphere. So if you take a sphere, you puncture it at these 4 points. These two mappings are not homotopic. You cannot continuously change one to another. So that's where this comes in. And maybe I'll also jump. This doesn't matter. Okay, I just want to mention this is joint work with my PhD student and a postdoc. And among the findings, you can also find ICORE. Okay, anyway, thank you.